Hi friends, welcome to follow up. Let's have a look at problem 338, counting bits. This is today's daily challenge problem, which is an easy problem. So in this video, our goal is to practice a base, for example, decimal and binary, and bit operations and dynamic programming. So here the question is that, given an integer n, so we want to return an array answer of a length n plus 1. Such that for each I, answer I is the number of ones in the binary representation of I, right? Because given n, so the index runs from 0 up to n. So the total indices, the total number of indices is n plus 1, right? So here we have two examples. For example, this one we're going to have 0, 1, 2. For 0, the binary representation is 0, so you get 0, 1 bits. 1 is 1, right? You get 1. And 2 is 1, 0 in binary representation, so we get 1 bits. So you get 0, 1, 1. And similarly, you can do other numbers. So here, the thing is that this n can be very large. So if we compute using all the numbers or using while loop to count the bits, it might be not very time efficient. But in this video, we first do it in the verbose fashion, and then we do it using dynamic programming. So our purpose here is to do some practice. First, so this is basically the pop count. In the first version, I'm going to write a function that transform a number to base 2, and in between we are going to count the number of 1 bits. So let's do it here. Let's see, do 2 base 2, right? So here we accept a number. Let's say n anyway. In this case, so what we want to do is that let's do a count. So it's 0. Then well, n is greater than 0. So what we want to do, we want to do integer division. So each time we divide by 2 and check the remainder. So let's do like n and r is def mode, right? So we divide n by 2. So here we write the quotient as n. In other words, we simultaneously updated this n. This r will be the remainder, right? So if r is not 0, right? So we are going to increment the count by 1. So this way, after the while loop, so we have already counted all the 1 bits in the number n. So we are going to return the count. So this is our hyperfunction. Actually, there might be some built-in functions in Python or other programming languages you can directly use. But here we use a while loop. So here the time complexity for this is obviously logarithm 2 of n, right? So you can write logarithm n. It's just up to a constant. So with that said, basically we can prepare the return. So we can initialize a result a variable. It's an empty list. So we are going to return its final state. And then for n in range, so because the number count from 0 up to and include num, so we're going to do num plus 1 here. And then, so basically result append the corresponding counts of 1 bits in this number. So that is 2 base 2 n, right? And then we just need to return the result. So this is one way of solution. So let's look at the test. Yeah, it passes all the tests. But here, let's see. Actually, we can do a quick time complexity analysis here. So here for version v1, let's call it version v1. So for v1, so the time complexity actually is nothing but summation, right? With summation, let's say we have a general n. So this will be logarithm n, right? Logarithm n. But with summation for logarithm n, so from say n equals 1, right, to let's see for I. Let's write it as I from 1 to the n or n plus 1. So let's use this num or as n, right? So n. So this is basically a summation of logarithm, right? So if you know integration, so basically you can get this will be a summation of logarithm, say 1 times 2 times I times times n, right? And then basically this will be something like so this will be logarithm n factorial, right? So this basically you can do a starting approximation is roughly n minus n plus 1 or something. So this is roughly O n logarithm m. So here we compute all these things up to a constant. So this V1 is O n logarithm m, right? So if you do not understand this step, so this step basically we used starting approximation. So this is one version. So here I want to translate this version a little bit. So maybe we just copy all these parts. And then so when we write this function, so here we use division. And if you like, so basically you can do some bitwise operations. Let's see, you can do something like this. N add equals n minus 1. So this will also work out. So let's first do a test and then explain the function. So it's wrong answer. Let's see. Well, so this is non-zero. Let's see. Then we are going to do this this m, and then we do we didn't update this count increment by 1, right? So now let's test again, right? Here we get this one. So this basically counts the bits. So here let's use an example. So I'm going to call this one version v2. But for version v2, let's explain the pop count function. So here let's explain what's the role of n equals n. So bitwise add with n minus 1, right? So let's use two numbers to demonstrate this point. First, let's use a number which is special. It's a power of 2. For example, we can use 4, right? 4 is 1, 2, 2 in binary, right? So we know the total counts, total bits of 1 is number of bits of 1 is 1, right? So now if we compute 4 and it's 4 minus 1, that is 3. So we compute 1, 0, and 0, and so 3 will be 0, 1, 1, right? So then we are going to get 0, right? Because this corresponds to 0, 0, 0, right? So then we get this 1. So now let's compute another one. So it's a little bit special, right? So we use 1, 1. So we know the number of bits of 1 is 2, right? So now if we compute, each time we do such a compute, we are going to increment the count. Originally the count will be 0, right? We compute 1, 1 and minus 1, that is 1, 0. So in the least significant bits, we have 1 and 0, so they cancel. So now we get 1, 0, right? So then we increment the count to be 1, right? So now let's now the number becomes 2, right? So now we compute and 2 minus 1. 2 minus 1 is 1, that is 1, 0. So again, so we compare the first bit. So we have 1 and 0, you're going to get 0. And the least significant one, you get 0 and 1, you get another 0, right? Then we get 0 after the stop condition. But in this case, we did another such operation. And so bitwise add, we increment by 2. So now the number is already 0, we stop, right? So we get 2. So that's the explanation for this version of function 2 base 2, right? So in other words, when we do the division by 2 in a cascading fashion, so each time if the remainder is 1, we count it. If it's 0, we just ignore. Then we get the number 1 bits, and then we get the result. So this is version 2. So now let me copy this one and explain a solution based on dynamic programming. So with the explanation above, basically we have a better understanding about this problem. So now let's look at how we can compute this more efficiently, right? So here, let's see. First observation is powers of 2 will be very special. It's special because this kind of number, it contains only 1 bit. For example, 100 is 1 bit. So 1000 anyway. So let's use this one. This is nothing but 2 to the power. This is the 2 to the power 1, 2, 3. This is 8, right? So this is the binary one. All this kind of this is 8, not 0. So they have 1 bit. So total number of bit 1 count is 1. So any power, right, of 2 has such a count. So then actually we can do this. We can use this already known count to compute some other counts. For example, let's start from 0. From 0, the binary representation is like this, right? So the number of bit count will be 0, and the 1, the count will be something like this. Then the number of 1 bits is 1, and 2, what we get is 0, 1, 2. And 2 is very special because 2 is a power of 2, so we get to this the 1. And then if we have 3, so what do we get? So 3 is 1, so 0, 1, 1, right? Then we get 2 bits, right? So now, we from 0 to 1, so actually if we add, we can compute 2 and 3 if you ignore the first most significant 0. So up to now, basically we can continue, right? So we can continue to compute other numbers with the already given one. So we have this, and then if we consider adding 1 here, so to each of this number, or adding the most significant one, the 2 to the power, add this one. In the first 0, we replaced by 1, corresponding to add 4, right? So we get a 0 plus 1, change this one to be 1, right? So what we get is 4, right? 4 is nothing but 1, 1, 1. So this 4, due to the fact that it equals 0 plus 2 to the power 2, it increased 1 bit. So here count is 0. So here count will be 1. And then we compute 5. So 5 is nothing but 1 plus 2 to the power 2. So we get 1, 0, 1. So they differ by 1 in 1 bit count. So we get 2. And then we can compute 6, right? 6 is this one plus 1 plus 2 to the power 2. So we get this, right? So this, because 2 have bit count is 1, so here we get 2. Now let's look at 7. So when we compute 7, so we are going to change this one to be 1. So what we get is 1, 1, 1. So because this 3 has 1 bit count 2, so this will have 1 bit 3, right? So up to now we computed from 0 to 7. Then we met another power of 2, right? That is, so next will be 8. That is 2 to the power 3. That is 1, 0, 0, 0. So this we can produce from the previous ones by adding the most significant one. So for example, we have 8. 8 is this one. We add a 1 bit. So we get 0, 0. So this has bit count 1. And 9. 9 is 1 plus 8, right? So here we have 0, 0, 1. So in binary, it will be adding 1. So we get 0, 0, 1. So then the corresponding bit count will be 1 plus 1. That is 2. So similarly, you can compute 10. 10 is this one plus 8, right? So we get what do we get? We get 1, 0, 1, 0, right? So this will have 2 bits because this one has 1 bit. So let's compute several more. So 11. So we get 0, 1, 1, 0, 1, 1. So in other words, we add one most significant bit in front of 3. So because this 3 has 2 1 bits, so this will have 3 1 bits. So now we can compute 12. So 12 is basically this one, right? So we get 1, 1, 0, 0. So the 4 have 1 1 bit, so this will have 2. Now 13 will be 5 plus 8, right? That is 1, 1, 0, 1. So because here we have 2, right? So then we get 3 here. Now we can compute 14, right? So 14 is going to 6 plus 8, so we get 1 most significant, then copy this 6. So we get 1, 1, 0. So we get 3 1 bits because here is 2. So now let's compute 15. So 15 will be something like this. 8 plus, so we get 1, 1, 1, 1, right? So here we have 3 1 bits. So here we get 4. So then next, what we get? We get 16. So that is 2 to the power of 4, right? That is 1, 0, 0, 0, 0. You can imagine. So here we have 0, 0, 0, 0, 0, 0, 0, 0, and all these numbers are 4 bits. And then you can continue the fashion, right? You get 16. So it's corresponding to add 1 most significant from 0, right? So you get 1, 0, 0, 0, 0. So because 1, this 0 has 0 1 bit, so here we have 1, right? Then you continue for 17, right? 17 is this one plus a 1 most significant one. So that is 1, 0, 0, 0, 1. Because originally 1 has 1 1 bit, so here we have 2, right? You just continue this fashion, right? So this will be our dynamic programming digest. So now let's look at the coding part. So in this part, I'm going to use DP. So the recursion relation basically is this. So you have a number, right? So then we add a most significant 1. Then we add the number of 1 bits increases by 1. So for example, we have a formula for n 1 bits, right? And 1 in binary. So if we have a number, let's see x, and then we plus some 2 to the power m. So this 2 to the power m will be larger than x. And then the number of 1 bits is the number of 1 bits in x plus 1. Right? This is for sure due to this most significant position. If 2 to the power m is greater than x. Right? So this will be our DP update rule. So you can digest using the above computations. We feel that we compute sufficient large number of examples. Now let's look at the coding part. So for the coding part, let's first get a result. The result will be, let's write 0 times n plus 1. So for 0, actually it's just 0. We don't need to care too much about it. So we can specify is x or c here, right? And then we can specify 1 power of 2. So originally it's 2 to the power 0, right? 2 to the power 0 is 1. And then what we want to do, so well, this b is less than or equal to n. It is possible that n is a power of 2, right? What we want to do, we want to generate these numbers here. So we can do this like, well, x is less than b, and x plus b is less or equal than n, right? So we want this in bound, and also we want this x is less than b, so that this b, notice that is a power of 2, as we mentioned here. You can regard this 2 to the power m as b. Then if this is the case, what we want to do, so we want result x plus b will be result x then plus 1, right? Then we can increment x by 1, like here, right? So we compute 17. Then next time we consider 18. 18 will be this is the 1 0, so it's going to be let me directly add this 0 0 0 1 0, right? So it's corresponding to 0 1 2, right? 2. So here it has 1 bit, so here we have 2, right? You can continue this fashion. Once you match a power 2, you just double it, right? So now we have this one, and then after this while loop, so we are going to reset this x to be 0, and then what about b? B multiply equals 2, or you can use bit operations like b towards the left 1 unit. So this is the same thing. So b multiplied by 2, right? So then we can return the result state. So this is the DP solution. So before we make any further comment, let's first do a test. So here n, here we write num, or you can use num as n. So let me do things like this. It might be better, right? Yeah, it passes 1. Now let's look at generic case. Yeah, it passes all the cases. So this will be the dynamic programming solution. So you can try to analyze the temp complexity and compare with the first version. So I guess for this problem, that's basically about it. Thank you.